dialogue management-based machine learning. So as usual, then the giving a presentation between 25 to 30 minutes. Then there will be rounds of questions from the audience and the committee. Okay, you may start.
Thank you so much. Hello all, I welcome you all for my thesis presentation. So my topic is an improved approach of intention discovery with machine learning for POMDP-based dialogue management. So this is the outline which I am going to discuss today. Starting with the introduction part. So the first thing is human-computer interaction. So the question is, what is HCI? So the focus is on interface between the users and the computers. So the human, with the use of brain and the different senses like eyes, ears, hand movements, gesture, and the speech, communicates with the software, which is the computer, using the keyboard, mouse, or joystick, or microphone, etc. And input is mapped inside the system, and the process is performed. Then output is given to the user with the help of speakers and the displays, etc. So this whole loop of one interaction called is human-computer interaction. It could be a continuous cast of different kinds of interaction. And HCI is situated at the intersection of computer science, behavioral science, and the design. And it helps in solving difficult challenges like supporting complex tasks, mediating network interaction, etc. Next part is ECA, Embodied Conversational Agents. So ECAs can be called as artificial agents or the intelligent agents. So ECAs have the embodied body, like graphical body, but unlike the robot architecture, they do not have any physical body. They just are embodied in a virtual world, but they are very capable enough to communicate with the users using facial expression, gestures, emotions, etc. Then Avatar is the second name for the ECA, and it is also a graphical representation of one person's alter ego or character, anime character, etc. And it can process the natural language. It can take natural language as an input and process the keywords to show the to display the outputs with the same kind of context and using the database. Now the main thing is how user and the ECA communicates. That is where the dialogue management comes. So for their communication or the interaction or conversation, we need some sort of a medium called dialogue management. So the dialogue management is a system consisting of a dialogue manager which helps in tracking the dialogue states and maintain a dialogue policy which decides how the system reacts on a given dialogue stage. So it is statistical approach in the modeling of the dialogue manager. So there are a few examples like tutorial dialogues. So we assign the reward that for the student, the increase in the mark, like student grades, should be the reward. That's how we communicate with the user. In the information seeking dialogues, the reward could be the positive if human receives the information as per desired output, and there could be also a negative reward if possible. There are three different kinds of dialogue management which I'm going to discuss today. The first is finite state machine, which has clear structure. It is easy to develop to effectively control the dialogue process, but it is not suitable for a complex dialogue task. The second is the frame based, which has advantages like it can handle more complex inputs and dialogues turn out to be like unnatural. That is one of the limitations. And the third is POMDP, which is partially observable Markov decision process. It is very popular in theoretical studies, and it is proven to be good model to deal with uncertainty. That is what I am targeting today, the uncertainty, because when human communicates with the agent, there is always uncertainty. There is nothing predictable or determined sets of communication existing. The disadvantage as of now is it cannot handle multi-topic tasks, and tagging and training corpus they are quite expensive and time consuming. So we need to think of that as well. To understand the POMDP, we need to have a look at the MDP. So MDP stands for Markov Decision Process. It has Markovian property. So MDP is an output of the continuous cast of dialogue management, which has the compound state of finite state of interactions using like agent feeds action to the user using continuous multivariate belief state space, and the reward function is applied. MDP is a phi-tuple process. S stands for the states, A stands for the actions, P stands for the probability of action A at the time t for the state S, and when the time step is changed to t plus 1, then the state is S test. Then the next is gamma, which is discount factor, which helps in maximizing the future sum of rewards. And the limitation of MDP is it cannot optimize in the stochastic environment, because when it comes to the policy, we need the POMDP to work with the uncertainty. So talking about the background and the literature. So the first thing is the partially observable Markov decision process called POMDP. So in the MDP context, assume state S is known when action is to be taken, otherwise policy cannot be calculated. So this is the limitation from the previous section. But if the assumption is not true, then it will be partially observable. That comes the POMDP model. So POMDP is the generalization of MDP, and the assumptions made in this context are agent models decision process using the MDP dynamics of determination. And POMDP framework is general enough to model a variety of real-world sequential decision process. So it can beat the decision processes like BFS, DFS, A-star, hidden Markov model, any Markovian property, including the MDP. And POMDP has 7 tuple process, which I'm going to discuss in the next slide. The only limitation as of now we have from the traditional POMDP model is, because of the Markovian property it is completely memoryless. So all the important information from the previous communication or conversation is lost. So we cannot have the important information while considering the next action. So that is why we need the belief state history, which I'm going to discuss very soon. So POMDP has 7 tuples. S stands for states, A stands for the action, T stands for the conditional transition probabilities, R stands for reward, omega stands for the observations, BGO stands for the conditional observation probabilities, and gamma stands for discount factor. Now the next is fuzzy logic. So the fuzzy logic is a system where we get the output in terms of real numbers between 0 and 1. It is a form of many valued logic. It is always about the truth value when generating the output, the crisp output from the fuzzy logic system. So we employed the fuzzy logic system to handle the concept of partial truth. It could be completely true or completely false between 0 and 1. So fuzzy logic system has 4 different modules. First is fuzzifier, second is inference, third is rules, and fourth is defuzzifier. So when user sends the state, maybe your user import from the observation made, they send the crisp inputs to the fuzzifier system. So this fuzzy set has different kind of entities like linguistic variables, linguistic terms, and membership functions. So using these 3 techniques, we can do the fuzzification on the given user import. Then inference is made using the predefined rules by the author for this particular system, and then we perform the defuzzification using the membership function, and then we get the crisp outputs. So next is belief state history. Now to overcome the limitation POMDP has, which is Markovian property of memoryless conditions, we need belief state history to store all the belief states we had previously during the communication. We need to store them so that not all the important information is lost, and we can use all the information while making the next action. So belief state is a probability distribution over all possible states, which gives as much information as the entire action observation history. So it is ongoing loop, like user sends the observation to the agent, and agent sends the action to the user back. So this is the ongoing loop. So for this entire history, we should be having the previous history so that we can only observe from the belief state history database. So as I discussed already, that using the dynamics of belief state history and outperforming the shortcomings of traditional POMDP, we can generalize the new model which can retain the advantages of current POMDP-based approach using the belief state history. Like as I discussed, like history information of observation and actions are not maintained explicitly, and that is why, because of the Markovian property, memoryless approach of POMDP, we cannot store any information. So this was the POMDP-based architecture, like traditional architecture presented by Bui. And as you can see, there is no sort of belief state history or database, some sort of thing, so that actions can be improved to improve the policy. But Dr. Yuan and team, they proposed a new approach using the knowledge-based database and the belief history database, so that we can not lose some important information. We can use all the important information from the user database with the communication with the agent. So now related work. First is trend analysis. So what is trend analysis? It is a widespread practice of collecting information and attempting to find a particular pattern or a spot of a particular kind of a trend, so that we can predict future events. We can even estimate some uncertain events from the past, that that could happen and what could happen next. So we can assume this kind of techniques. There are different kinds of approaches to perform the trend analysis. I'll be using the last one called wavelets. It is a mathematical transformations applied to transform data into a set of coefficients to analyze trend. And I'll be using the DWT, discrete wavelet transform, which is based on the mother wavelet transformation, and wavelet is called as small wave. So the small wave wavelets come from the mother wavelet. The mother wavelet comes from the Morlet wavelets and the Mexican head wavelets. So that is a combination of mother wavelets. So then we can perform the trend to find important pattern in the belief state history, I mean. So the next is survey part. I've referred few papers. I'll be highlighting some key points one by one. So the first paper is towards a generic framework for multi-party dialogue with virtual humans. So they have focused on multi-modal, multi-party dialogue management, action selection and timing-based mechanism, real-time acceptable interaction, and their aim was to follow candidate action in exceptional circumstances. The second paper is deep variational reinforcement learning for POMDPs. So they have proposed this DVRL model, and the DVRL allows agent to learn generative model. It solves POMDP for given stream of observation without any knowledge of latent state space. The third paper is deep decentralized multitask multi-agent reinforcement learning under partial observability. They were focusing on multitask multi-agent reinforcement learning under the partial observability using decentralized single task learning without any task identity, and single task policies were unified. The fourth paper was deep learning for dialogue systems. So they were focusing on conversation-based intelligent agent. Their model's core was all about the task-oriented dialogue systems, and they consist of language understanding, dialogue management, natural language generation, etc. The fifth paper is learning to communicate with deep multi-agent reinforcement learning. So they had proposed two different models called RIAL and DIAL. So reinforced inter-agent learning is RIAL, and differentiable inter-agent learning is DIAL. So RIAL focuses on deep Q learning, which we are going to see next. And one of the first attempt in communication learning and deep learning approach was given by this paper. And they presented some novel environments to learn the communication. Sixth paper is interactive reinforcement learning for task-oriented dialogue management. So they focused on interactive reinforcement learning. Agent receives action-specific feedback from user. So the feedback is the important thing, which I'm going to discuss next. Feedback helps in improving policy, and the feedback helps in learning new interactions as well. Seventh paper is dialogue manager domain adaptation using Gaussian process reinforcement learning. So they were focusing on data-driven machine learning approach, results based on limited domain application. Traditional approaches are outperformed, and they estimated uncertainty, which is very useful for reinforcement learning. And they proposed an elegant framework for Gaussian process reinforcement learning. And the last paper is distributed dialogue policies for multi-domain statistical dialogue management. So they have focused on hierarchical distributed dialogue architecture. GPRL-based reinforcement learning is used in constructing generic policies. Next is problem statement. So after we outperform the shortcomings of POMDP model using the belief state history and performing the trend analysis using the DWT, we were able to improve the intention discovery. But the next question is, how can we make the agent more intelligent in terms of generating natural dialogues? So there are different things which we should consider. First is goal-driven dialogue conversation. Second is sentiment learning. Third is policy improvement. So there is a need to implement constant learning for the agent so that we can optimize the dialogue length and we can reduce the dialogue length. So using the machine learning approach called reinforcement learning, which encourages a belief or a pattern like in terms of a behavior to provide some sort of rewards so it can improve next time. So this method is called trial and error. And using sentiment analysis and other techniques, we can reach the user's goal easily to improve the intention discovery in the context-driven communication. Next is proposed method. So first is sentiment analysis. So what is sentiment analysis? It is about the process of computationally identifying and categorizing the emotions expressed from a piece of text. So if you talk about speech, speech can be converted to the speech to text platform using speech to text APIs, or SDS, spoken dialogue systems, can be converted to the text. So I'm just generalizing text over here. Sentiment analysis helps in determining the intention using emotion discovery, and it helps in achieving end-to-end task completion scenario. So sentiment analysis can be targeted as a classification technique like binary. So positive and negative entities can be targeted, and multi-class categorization can be done as well using the positive, neutral or negative sentiment probabilities. So most approaches use the sentiment lexicon as a component. So we can use it for a general purpose or to extract some suitable corpus from the sentiment analysis. Next is reinforcement learning. So RL's main task is to produce fully autonomous agents that interact with their users to learn the optimal behaviors over the time using the trial and error system. So the definition of RL can be given as a principal mathematical framework for experience-driven autonomous learning by itself. So there used to be some limitations using like when you used to use the traditional RL, like memory complexity, computational complexity, scalability, but all of these are outperformed with the rise of deep learning and deep neural network and stuff like that, using powerful function approximation and representation learning properties. As we discussed during the MDP, this communication using the dialogue management is all about continuous cast of multivariate belief state. So why we need the function approximation? Because we are targeting the continuous cast of dialogue management. We are unlike limited interaction or information driven language, because we are just targeting users aim achieving goal. So that is why we need the function approximation. The true essence of RL is learning through the interaction, which is again the trial and error purpose. So as you can see in this architecture, this is the environment, like we can also call it a user. This is the agent, we can also call it a system. So first of all, at the time t, the agent receives the state S, and then agent using the policy sends the action to the user again. Now when the transition happens, for the time st+1, the environment sends the state st+1 as well as the reward rt+1 to the agent, and then the policy is mapped and it is assigned particularly to one such states using the feedback of reward, and then new action at+1 is developed. So as you can see, this ongoing loop is known as perceptron action learning loop. So here I am using SASR format, which is inspired by the SARSA form of feedback provision technique. SARSA stands for state action reward state action. So here I am just considering I am SASR for my approach. So the dynamics of trial and error learning has its roots from the behaviorist psychology, and that is the main foundation of RL. And this whole system where we send the reward from user to agent, it's all about the feedback. That agents need the feedback that what agent has sent as an action to the environment, whether the agent was correct or not. So whether the agent was correct, the reward will be sent as a positive. If not, the reward will be sent with the negative probabilities. And this is equation for the deep reinforcement learning. The R represents the total return, that means total feedback. T represents the turn from, it can be called as time from 0 to t-1 or 1 to t+1. The gamma stands for discount factor, R stands for the reward, B stands for the dialogue state, and A stands for the action. Now for the RL, what technique I am using? The technique I am using is Q learning. The Q learning is another technique used in machine learning. The Q here stands for the quality of an action taken in a given state. So the Q stands for the cross product combination of state and the action to decide the quality of that particular loop. So that is what we call as a feedback, and that can be given as a reward to the agent again from the user's end. The Q learning can identify an optimal action selection policy for any given infinite exploration time, which could be partly random policy. So when we are targeting uncertainty using the POMDP, we need partly random policy, because there is no such finite state is there that we can decide that whether user has reached the goal or not. So for deep, there is some literature information. This has nothing to do with my work, but I have just added. So for the deep Q learning, the function approximator is used is the deep neural network. And the neural network is used to approximate the Q values in decision process. But this Q learning basically was launched for the Atari games, for the traditional Atari games, where the user and the agent, they didn't know which move the user is going to make. So that purpose, to realize the different moves from the previous states, they used to use the neural network so that they can compute the image and the moves of the object in the Atari game to compute the Q value. But I am just using this theory of Q learning for my feedback provision in my approach. This convolution layers has nothing to do with my work, but I've just added over here that how Q values are generated to show that only. So over here, this equation is the important which I'm using. First Q of S stands for the new Q value, where S is state, A stands for the action. The second Q of S stands for the old value. Here, as you might think that why there are like same terms are given, why Q and Q dash is not given? Because using the function approximation, we do not want to have the Q to increase the computational complexity. That is why we just update the value of state and value of action in the Q learning context. Alpha stands for the learning rate. We can call it a hyperparameter. The value can be assigned as 0.001. R stands for the reward. Gamma stands for the discount factor, and value can be assigned as 1, which helps in maximizing the future sum of rewards, as I have discussed already. This whole part is known as estimation of optimal future value, and this whole part, except the alpha, stands for learned value, so that we can predict the new Q value. Proposed architecture. Before that, I'll be comparing my work and the existing work to showcase my contribution. We used the traditional POMDP to find the optimal policy, and he was targeting the value iteration based POMDP, and the other approach he used was rapid dialogue prototyping methodology using factored POMDP. Now Mulpuri and Kaur, they used to be my seniors. So Mulpuri, what he did was he used automation of requirement elicitation in software product line, and he used a decision making algorithm for automation, and knowledge level used in addressing the policy, that how intention can be improved, etc. Kaur used the CA with emotions to offer better understanding while communicating with the users. She used the fuzzy logic system which used to generate the facial expressions, and she conducted the usability study to take a feedback from users that whether her work was feasible or not. Next is my work. I am extending the work of Mulpuri and Kaur. I am presenting the approaches like sentiment analysis and reinforcement learning, and the more details I will be discussing in the proposed architecture. So this was the architecture presented by Mulpuri, this was the architecture presented by Kaur, and this is my architecture. So over here, as you can see, the user communicates with this system agent over here using the POMDP model. So first of all, user sends the observation to the state estimator and the sentiment analysis. The state estimator then defines the belief state and stores that the updated belief state into the belief state history database. And then the triad analysis is performed over this history database so that we can calculate the number of change points, so that we can decide the knowledge level for that particular belief state from the particular belief state history and the current belief state. So the knowledge level can be fed to the policy selector module as expert or professional or amateur or the novice. The second part of the triad analysis goes to the fuzzy logic system. The number of change points are sent to the fuzzy logic system. Other part of the observation goes to the sentiment analysis. Then the rewards in terms of negative, neutral or positive, they are fed into the fuzzy logic system or fuzzy control system. Then the crisp output are fed to the ECA using the facial expression, and that final output is shown to the user using the action as well at the same time. The actions can be decided based on the policy and the COCOM. The COCOM stands for Contextual Control Model, and based on this COCOM we can decide that whether the policy was improved for that particular action or not. This is for the first loop. Now from the second loop onwards, as I told, that at the time t+1 we need to use the feedback called reward. So this feedback over here, it works as a reward from user side to the agent from the reinforcement learning approach which I have already shown to you. This is a little analysis that the sentiment analysis rewards like negative, neutral and positive will be used using the COCOM model to decide the emotion for that particular policy selection module. Now talking about the algorithm, these are different models which I've already discussed, so I'm just going to skip. Initialization, state estimator, feedback, trend analysis, knowledge level selector, sentiment analysis, fuzzy logic system, policy selector, making an action, and the end part. So these are the data sets and the tools which I'm going to use. So I'm just going to highlight the important ones. For the 3D models, I've used this library to load the 3D models inside the Android environment. And to generate the 3D models, I've used the FaceGen software. For the sentiment analysis, I'll be using NLTK Python library. For the word embeddings, I'll be using Word2Vec Glow, which is pre-trained model, because I'll be using the nearest neighbors of the words and the linear substructures. For the training dataset, I do have 7,500 sentences with the emotions and the 1,500 plus words to train with the emotions. And for the dialogues, I'm going to consider Con AI 2 dataset and the WizDial dataset, which has 354 million training dataset, 17 million validation datasets, and the 10 million testing dataset. For the deep Q learning, I'll be using TensorFlow and PyTorch. For the Wizard of Oz, I'll be using relational strategies in customer service dataset. And in the RStudio, I'll be using FuzzyR package, WaveSlim package, and the POMDP package. So the experiment and design, I conducted a communication interface between the agent and the user to calculate the belief, NCP, which is number of change points, and the knowledge level selection. So as you can see, for the first interaction, the knowledge level was novice, because this information from user's end is very nominal. It cannot determine the user's goal. Then from then onwards, it started becoming expert, and final policy was selected was expert. That means we were able to improve the intention discovery using the improvement in the policy. So this is the prototype environment. So this is the Android application which I have developed based on the architecture. So when you communicate with this ECA, so ECA will generate the emotions that can help user in communicating in a very well manner, so that even user can understand whether the ECA has understood the aim or the intention user has or not. So these are different expressions which I have shown. This is how I'll be showing that ECA can communicate while speaking. So this is the expression of hi, how are you, I'm fine, thank you, and nice to meet you, etc. So I got from sentiment analysis in few of the sentence. Using the FAMM approach, which I already discussed previously, it is a fuzzy associative memory matrix. Using this approach and the sentiment analysis output, I'll be using this sentence. Most automated sentiment analysis tools are shit. So there are two probabilities I received, negative and the neutral. The neutral has higher probability. That is why I have highlighted this in red with bold and italic. So as you can see, fear and sad will be decided from strategic and a tactical. Why strategic and tactical? Because the policy is expert. For the expert policy, we need this COCOM rewards like strategic and the tactical. Now from the fuzzy crisp output, it could be W2 or W5. We can assign the higher probability of fuzzy output to decide fear will be there or sad will be there for this particular sentence from ECA's end. I think I'm running out of time, so I'm going to just skip the challenges. This is the timeline which I'm just proposing, that I'm targeting thesis defense in April 2019. Conclusion can be made as I have done the preliminary implementation. Using the POMDP-based dialogue management, we can improve the intention discovery of users. Using the sentiment analysis, we can help agent understand the sentiment or the emotion from the user's import. Using the RL technique, we can learn the optimal policy. That was the main aim, and we can reduce the dialogue length, and we can make dialogue management conversation very smoother than the formal approaches. For the future work, I'll be performing experiments using the listed data set, tools and libraries, and additionally I'll be comparing my final results with already existing models, and these are few references. Thank you. Any suggestions or questions?